A-Level Paper 2, 2018. Alkanes can be used as fuels. We give an equation for the combustion of heptane C7H16 in excess of oxygen. So in excess of oxygen you get complete combustion, so you get carbon dioxide and water. Incomplete combustion gives carbon monoxide and water, or carbon and water. But in this case we're going to get carbon dioxide and water, so we have C7H16 plus O2 gives CO2 and water, and then we need to balance it. 7 C's, 7 CO2s, 16 H's, 8 H2O to get the 16 H's. Then I've got 14 O's, add 18 is 22, so I'll need 11 O2. Heptane can be obtained from the catalytic cracking. Identify a catalyst and a condition and equation for this process. So the catalyst zeolite, the condition is moderate pressure, so you don't need it too high. Moderate pressure, a couple of atmospheres is fine, 2 to 3 atmospheres is fine. Hexadecane C16H14 cracking to produce 1 molecule of heptane, 1 molecule of cyclohexane and 1 other product. So we've got C16H34 makes heptane, so hept is 7, so 7, double it is 14, add 2 is 16, so that's heptane. 1 molecule of cyclohexane. Cyclohexane is C6H12. Remember, it's got the general formula of an alkene, so you double it, C6H12, double the 6 to make a 12, because it's in a cyclic structure. And then 1 other product, and you can work out what that's going to be. Let's just check. 7 add 6 is 13, 16 C's on the left, so I've got 3. 16 add 12 is 28, 34, 28 take away, 34 take away 28 is 6, so I'm going to make propene. Alkenes can be used in free radical substitution reactions to produce haloalkanes. Give equations for the propagation steps in the reaction of butane to form 2-chlorobutane. So I've got Cl dot, and I've got butane, CH3, CH2, CH2, CH3. You always make HCl, always, and then that tells you what else you can make. So I'm going to make butane, but I'm going to remove an H from somewhere and leave a dot on the carbon that's lost its H. So I'm going to come back to that and work out why it's on carbon number 2. CH3, CH2, CH, CH2 adds Cl2. Always remakes a radical, so that's always remade a catalyst in the reaction, and then the Cl goes on to the point where the dots spin. So that is 2-chlorobutane, and it says here I'm making 2-chlorobutane, so the dot is there where it's short of a bond, and the dot is there where it's short of a bond. So I've put it onto that one there, removed the H from there, and made a dot, an unbonded electron, on carbon number 2, because that's where I want my Cl to be, because it specifies that I'm making 2-chlorobutane. Chlorofluorocarbons are a group of halogenoalkanes currently banned in many countries. The structure of a CFC is shown below. So I've got 3 C's and 3 F's. Identify the radical produced from the CFC that may be responsible for the depletion of ozone in the atmosphere. Explain with the aid of equations why a single radical can cause the depletion of many molecules of ozone. So the radicals are Cl dot. You always make a Cl dot, so Cl dot. And the explanation is that if I produce the equations for these, it says explain with the aid of equations. I've got a Cl dot plus O3 is ozone. The only other form of oxygen that there is O2, so that leaves Cl and O and a dot here. I'm going to balance the equation. This radical will react again. ClO dot with more O3 again makes O2, and this time, because I've got 4 O's on the left, I can balance it with 2 O2s, and then that makes a Cl dot again. So the Cl dot is regenerated, and that's why one single radical can cause the decomposition of many moles of ozone, because it's regenerated, and it causes this chain reaction to keep on decomposing ozone. Question 2. Halogenoalkanes are useful compounds in synthesis. I've got a synthesis pathway here, reaction pathway, starting with this chemical. CH2O, CH3, CH2Br. So I've got 1, 2, 3 carbons in a line, so I've got propane. I've got an ol, so I've got propan, and the ol is at number 1. Propan 1 ol with a Br, a bromo at 1, 2, 3. 3 bromo propan 1 ol, and I've got a methyl group on there. The methyl group can actually only go on number 2, so it's 3 bromo, 2 methyl, or just methyl propan 1 ol. Explain why a halogenoalkane is attacked by a nucleophile in this reaction, reaction 1 nucleophilic substitution. So what you've got is you've got sodium hydroxide in cold water, and the OH minus, the lone pair of electrons on the O of the OH minus, is attacking the C of the Br. It's because the Br is more electronegative than the carbon, so that's creating a polar bond here with the delta plus on the C, and the lone pair of electrons on the O is attacking that C plus and bonding with it, so it's donating its lone pair of electrons into a covalent bond then to the C. That's because that's a nucleophile, a lone pair donor. Br is more electronegative than the carbon, good. C has a delta plus and Br has a delta minus. The lone pair on the OH minus is donated or attacks the C delta plus. The infrared spectrum of compound Y shows a significant absorption in the range 1680 to 1750. If you look that up, that's a carbon to oxygen double bond. Draw the displayed formula of Y. So if I've got a carbon to oxygen double bond, this OH minus has been turned to a carbon oxygen double bond, so that's made an aldehyde at that end, and if it says it's significant, it's probably got this one converted as well. So both of those OHs, both those alcohols, have been oxidized to aldehydes, probably with something like so it's here, this has been oxidized here in reaction 2, probably by something like acidified potassium dichromate. There we go. So the OHs have been oxidized to aldehyde groups at carbons 1 and 3, and we've still got the methyl group at number 2. Compound Z has the empirical formula. Now remember, an empirical formula doesn't necessarily mean that's its molecular formula. It could be double or triple that. So if it's C3H4NO, well, there's 5 H's in that already. There's 2 O's, so I think it's double that. C6H8N2O, 2 N's and 6 H's. So if I've got 4 C's and it's going up to 6 C's, then I've got CN's attacking. So I've got CN minuses, potassium cyanide is attacking these aldehyde groups. If a CN minus attacks these aldehyde groups, the CN minus joins on. It joins on, the CN minus has got a lone pair and it attacks the delta plus on the C. The lone pair of electrons goes on to the O, makes an O minus, and then the lone pair of electrons on the O then bonds with an H plus, and that's why you need potassium cyanide and dilute acid, because the H plus bonds with the OH minus once the CN has bonded on, and you get 1 on each end. There we are, there's the 2 CNs. I've got the 2 OHs formed from the CO double bond, and I've got the rest of the molecule intact. Question number 3. The oxidation of propan 1-ol can form propanol and propanoic acid. So you're going to oxidize it with an oxidizing agent, probably something like acidified potassium dichromate, and reflux it. Keep heating it until it makes propanol and propanoic acid. The boiling points are shown below. So I've got 3 different boiling points of propan 1-ol, propanol and propanoic acid, and it said then the aldehyde, the propanol, can be separated from the mixture by distillation. Explain with the reference to intermolecular forces why the distillation allows propanol to be separated. So I've got to talk about intermolecular bonding within each of these and explain these boiling points. So first of all, propanal. Propanal has got dipole-dipole attractions because it's got a polar carbon to oxygen double bond, and a relatively low boiling point therefore. Propan-1-ol has got hydrogen bonding and therefore a higher boiling point. Propanoic acid has actually got dipole-dipole attractions and hydrogen bonding as well, and therefore the highest boiling point. How could it separate out? Well, propanal has got the lowest boiling point of them all, so as long as I keep, when I'm distilling it, the temperature below 97 degrees C, then this will boil, but the propan-1-ol and propanoic acid won't boil. Give two ways of maximising the yield of propanal obtained in the distillation of reaction mixture. Well, I've just got to keep the boiling point below 97 degrees C so that the propan-1-ol doesn't start boiling and the propanoic acid doesn't start boiling either. Another way, I could cool the collection flask. So if I cool the collection flask, that's going to help the ethanol vapours, the propanal vapours, the propanal gas condense in the collection vessel. Describe how you carry out a simple test tube reaction to confirm that a sample of propanal contained does not contain any propanoic acid. I'd use sodium carbonate. If there's any propanoic acid in the mixture, the sodium carbonate will produce bubbles or effervescence. The student carried out an experiment to determine the enthalpy of combustion of ethanol, and I've been given a specific heat capacity. So I know the equation that I'm going to use. Q equals mc delta T, so delta H equals minus mc delta T. So let's have a look at the temperature change. Am I given the temperature change? No, I've got to work it out. So let's work out the temperature change so far. It's gone from 25.1 to 40.2. Subtract the two. It's gone up by 15.1. So I've got the specific heat capacity. So Q equals M, which is the mass of water. So remember, it's the mass of water, it's not the mass of the ethanol that's being burnt, it's the mass of the water that you're heating up, and it's in grams. 150 multiplied by the specific heat capacity multiplied by the temperature gives 9467.7 joules. Now it's in joules because the specific heat capacity units are in joules. It eventually wants in kilojoules, so if I go small unit up to a bigger unit, I'm dividing by 1000, divide by 1000, 9.4677 kilojoules. That's the heat that's given out. So now I've got to work it out per mole because it wants it per mole. So it says kilojoules per mole. So the moles of ethanol burnt, I've got to work out how many moles of ethanol I've burnt. I've got 457 milligrams. I've got to get that into grams because moles is mass over mR. So 457 milligrams, if I take milligrams up to grams, if I'm going from a small unit to a bigger unit, I'm dividing by 1000, so it's 0.457 grams. The mR of ethanol, I can work that out and it comes out as 46. So the moles of ethanol burnt are 9.93 times 10 to the minus 3. I've got a small amount, so I'm going to have to scale up. So that I can work out how much I need to scale up by to get 1 mole, I do 1 divided by that and it'll come out with a number, and I multiply that by the value of Q. So this amount of energy is released when 9.93 times 10 to the minus 3 moles are burnt. So what I do is I do 1 divided by that value, and that will give me a number that I scale up by. I'll multiply by the number of kilojoules, and that tells me the amount of heat energy released when 1 mole are burnt. 952.99 kilojoules per mole, and that should be a negative value. It should be negative, and all of my other values are to 3 significant figures, so I'm going to round that up to 953, so minus 953 kilojoules per mole. Question 3.5. A mixture of alkenes is produced when pentan-2-ol is dehydrated in the presence of hot concentrated sulfuric acid. So concentrated sulfuric acid removes water. It removes an OH from a carbon and an H from a neighbouring carbon atom. So between those two carbon atoms there's an H on one and an OH on the other carbon atom, and it removes the water from across those two carbon atoms and leaves a double bond. Pent-1-ene is one of the isomers produced. Name and outline a mechanism for this reaction. Well, if I'm removing something like water, it's an elimination reaction. So what actually happens is, if I draw pentan-2-ol, so 5 carbons in a line with the OH at number 2, I've got a lone pair of electrons on the O, attacks H+, which is the sulfuric acid. Sulfuric acid, all acids make H+, and then what happens is the O bonds to the H, and the O gets the plus. So the electrons are moved onto the H+, so it loses its plus, and the O has electrons move away from it, so that gets the plus. Then I need to break the water off, so the water breaks off and the bond breaks here, and the electrons go onto the O, so that removes the plus on the O and makes H2O, and then one of the H's on the neighbouring carbon then breaks off. It could have been this H here and made a double bond there, so there's no reason it has to be an H on the left. It could be one on the right, except the question says it makes pent-1-ene, so this will make pent-1-ene because it'll make a double bond then between the two. So that's the mechanism there. A pair of stereoisomers are also formed in the reaction in question 3.5. So as I've said, you could, instead of the double bond being here, pent-1-ene, you could have made pent-2-ene, because this hydrogen could have broken off to make the double bond here and kept the CH3 here. So if I'd made a double bond there instead, I would have made pent-2-ene. Now there's two forms of pent-2-ene, there's Z and there's E, because there's no free rotation around that double bond, so the atoms get fixed in positions in space. No free rotation about the carbon-to-carbon double bond. Each carbon in the double bond has two different groups attached, and the groups get fixed in position in space. Now, which of the two? It says a pair of stereoisomers are also formed. Name the less polar of the two. So the less polar of the two. If you have two groups on the same side, on a Z, then these groups can be polar, and so it pulls the polarization, it pulls any delta plus and delta minuses onto one side. So a Z isomer is always more polar because you've got two groups, like two methyl groups or a methyl group and an ethyl group, they actually repel electrons, but it doesn't really matter. Those two groups may be polar and it pulls the polarization onto one side. If they're opposite in an E isomer, then the polarization is spread. So an E isomer is always less polar than a Z isomer. Question 4. Compounds A and B react together to form an equilibrium mixture containing compounds C and D according to the equation. A beaker contains 40 cm cubed of 0.16 mole dm solution of aqueous solution of A. So first of all, I'm looking at this and thinking, well, I can convert that centimetre cubed into decimetre cubed by dividing by 1000, and I've got a concentration, and concentration is moles divided by volume. I can work out the number of moles of A. That's the first thing I'm thinking. Then I've got number of moles of B. I've got number of moles of C in the reaction mixture are added to the beaker. It looks as if I've got no D, and allowed to reach equilibrium. I need a table, so let's get a table. So concentration is moles divided by volume, so 0.16, which is my concentration, equals moles divided by 40 centimetre cubed into decimetre cubed, small unit into a large unit, divided by 1000, 0.04. I've got the number of moles of A is 6.4 times 10 to the minus 3. So I need this table here now. So at the start I've got 0.0064 or 6.4 times 10 to the minus 3 of A. I've got 0.0095 of B. It tells me that in the equation here, in the question here, 9.5 times 10 to the minus 3, and I've got 2.8 times 10 to the minus 2 of C, and I haven't got any D. It doesn't tell me anything about D, so I'll have to assume that I've got no D. It tells me at the end I have 3.9 times 10 to the minus 3, or 0.0039 of A. So my first job is to work out how much of A has gone. So 0.0064 take away 0.0039 is 0.0025. 0.0025 of A have gone from the start to the end. So if 0.0025 of A have gone, 2 moles of A react with 1 of B, 2 to 1. So for every 2 moles of A reacting, 1 mole of B will react. 0.0025, divide that by 2, 0.00125 of B have reacted. Okay? 0.00125 moles of B have reacted. So 0.0025 moles of A have reacted, 0.00125 moles of B have reacted. For every 1 B, 3 C are made. So I'll multiply that by 3, 0.00375 will give me the number of C that are made. For every 1 B have 1 D is made, so 0.00125 makes 0.1125. Now I need to work out what's left in the mixture at the end. Left in the mixture at the end of A is 0.0039, I was told that in the question. Started off with 0.0095 of B, I've used up 0.00125, so I've got 0.00825 left. C, I started with 0.028, and I've made an additional 0.00375, so if I add the two together I make 0.03175. And D, I didn't have any to start with, and I've made 0.00125. Give the expression of the equilibrium constant. So what I do is I take C, concentration of C, and I raise it to the power 3, that's number in front. Concentration of D raised to the power 1, or just itself, divided by concentration of A squared, divided by concentration of B. Before I do question 4.2, I just want to point out that the units are moles per decimeter cubed on 4.1 that I missed off on the last video. So I've got moles per decimeter cubed, moles divided by decimeter cubed as a concentration. I've got 4 concentrations on the top, and I've got 3 concentrations on the bottom. So 4 concentrations on the top divided by 3 concentrations on the bottom leaves 1 concentration on the top, 1 mole per decimeter cubed on the top. Let's have a look at 4.3 then. So what have I got? I've got an equilibrium, an expression for the equilibrium constant. Equilibrium constant is concentration of C to the power 3, concentration of D, divided by concentration of A squared, divided by concentration of B. So let's put those numbers in. So let's put the numbers in. I've got a value of 116 for K. I've got a value of C, I've got a value of D, and I've got a value of B. I've not got A. I need to find A. So what I can do first of all is I can move A squared across the equal sign from the bottom up to the top, and the KC across the equal sign from the top down to the bottom. So I put the KC on the bottom there by moving it across the equal sign down onto the bottom, and I've taken the A squared from the bottom up to the top. So now I've got an expression for A squared. I've got the concentration of C is 1.05. I've got the number of moles, by the way, so moles is concentration is moles divided by volume, and I need to divide by the volume. The volume is 5.00, so 5 times 10 to the power of 2 centimeter cubed. We've got to get into decimeter cubed, so I divide by 1,000 to get centimeter cubed into decimeter cubed, 0.5 decimeter cubed. And so I can divide each of the moles of C, the moles of D, and the moles of B by the volume. The reason I need to divide by volume is because I've not got equal number of moles on each side. I've got 2 moles of A and 1 of B, so that's 3 moles on the left, and I've got 3 moles of C and 1 of D on the right. I've got 4 moles of D on the right, so the volumes won't cancel when I divide by them because I've got different numbers of moles on each side, and so when I divide by volume that will need to be done. A squared is 0.029289, square root it 0.17. It's got to be to 2 significant figures because I've got some of the values to 2 significant figures, such as 0.21, 0.076. So my lowest value, so some of the values are to only 2 significant figures, so it needs to be to 2 significant figures. Justify the statement that adding more water to the equilibrium mixture will lower the amount of A in the mixture. That's difficult for 3 marks. So first of all, you need to say that adding more water will lower the concentration of everything. Then what it does is, Le Chatelier's principle says opposes any change. So any lowering of concentration means that the concentrations have got to rise. It needs to make more moles of chemicals. And the side that's hit most, the side that's most affected, if you lower the concentration, is the side on the right, because that's got more moles. 3 add 1 is 4 moles. On the left, there's 2 add 1 is 3 moles. So on the right, the lowering of concentration affects the right more than it does the left, because there's more moles on the right hand side. So concentration needs to be raised by making more moles of the right hand side, because it shifts to the right hand side, because the right hand side has more moles and needs more moles making, because the moles, the concentrations have been lowered by the addition of water. Tough question, that. Question 5.1. Then I've got an equation and I've got a rate equation. So from my rate equation, I should be able to, if I've got a full set of data as I have in question 1, I should be able to work out the rate constant. Work out a rate constant from experimental data number 1. Give your answer to the appropriate number of significant figures. Well, what I've got first of all is, if you notice some of these figures, then they're all to 2 significant figures. 2 significant figures, ignore the first 0 and then count the numbers thereafter. They're all to 2 significant figures. So what have I got then? Rate equals K multiplied by the concentration of BrO3 multiplied by the concentration of Br and multiplied by the concentration of H plus squared. So let's take experiment number 1. Rate equals 0.024. There it is. 2.4 times 10 to the minus 2 equals the rate constant. I don't know that. And then I've got the concentration of BrO3, which is 0.1. The concentration of Br, which is 0.2, and the concentration of H plus, which is 0.3, and the 0.3 needs to be squared because it's given that in the rate equation. So 0.024 equals K multiplied by 0.0018. I'd multiply all those out first of all and get your number here, and then K then equals 0.024 divided by 0.0018 equals 13.3, and I've put it to 2 significant figures by rounding it down to 13. Complete table 2. So now that I've got K, I can just work out the missing amounts. So rate I've got equals 13, which is my K. It says they're all carried out at a given temperature, so the temperature is not changing. K only changes if you change the temperature, so if the temperature is staying the same, then K is going to stay the same at 13 throughout the whole experiment. Multiplied by concentration of BrO3, I don't know that, so I'll put a question mark there. And then I've got 0.2 and 0.3 and 0.3 squared for the H plus. So 0.2 and 0.3 times 0.3. I resolve that then, and I'll work out as 0.15. This one here, I don't know the rate, so the rate equals 13, but I've got 0.2 multiplied by 0.4, multiplied by 0.5, multiplied by 0.5, so I've got this value squared. Work it out, it equals 0.26, and I've put it to 2 significant figures again. Third one here, I've got the rate, 0.027 equals 13, the rate constant, multiplied by 0.1, multiplied by 0.1 here, and I've not got the value of H plus squared, so I've got 2 question marks in here, H plus squared. 0.027 divided by 13 divided by 0.1 divided by 0.1 equals 0.2077. Square root it, 0.45. They allow 0.45 or 0.46. Got to be to 2 significant figures. Question 5.3 and 5.4. I've got the Arrhenius equation here. and what it wants me to do first of all is take temperature and divide 1 divided by temperature. So 302 divided 1 divided by 302 works out at 3.31 times 10 to the minus 3. For this one here, it's got 1 divided by t, and so here I need to do ln 1 over t, and so a natural log of 1 over t is natural log of 3.7 times 10 to the minus 2, and it comes out as minus 3.30. Okay, so now I've got 1 over temperature here. I've worked out 1 over temperature, and I've got 1 over time here, and I've got natural log of 1 over time. You don't need to worry too much about why we're doing this. We're doing this to fit in with this equation here, but it leads you through. It'll always lead you through. It now asks you to draw a graph, and it asks you to draw a graph to plot a graph of 1 over t is the y-axis, ln 1 over t, which is this one. So you've got to plot these points on the y-axis against 1 over t, which is the temperature on the grid. And so it will look a little bit like this. You get a straight line graph where here you've got natural log of 1 over time, and you've got 1 over temperature along the x-axis. And as long as you use at least half the graph paper, plot the points correctly and put a line of best fit, you'll get 3 marks for the graph, and 2 marks just filling out the table. So where are the other marks from then now? So you need to work out activation energy. The next thing you've got to do is work out the gradient. If you work out the gradient, that's how far down it's gone divided by how far across it's gone. So you draw a triangle. If you draw a triangle and measure the height and divide by the width, then you should end up with a number that's in the region of 6640. It's a minus number because the line's coming down, and that equals minus activation energy divided by R, which is 8.31. That's just something to remember. When you plot these graphs, when it asks you to plot these graphs, the gradient equals minus activation energy divided by 8.31. If you want an explanation of that, then I give an explanation of that in the previous video on 2017 paper. I can reverse both sides, so now 6640, there shouldn't be a minus there. Activation energy is 6640 multiplied by 8.31, so I've taken the 2 minus signs away from each side, so 6640 multiplied by R, which is 8.31, equals the activation energy 55178, and it's in joules per mole. And then I need to turn it into kilojoules per mole by dividing by 1000 and rounding it up to 3 significant figures, because all of the other numbers are in 3 significant figures. How do I know that's in joules rather than kilojoules? Because it tells me here that R is in joules per Kelvin per mole, so that's in joules, so this must work out in joules. I need to convert it to kilojoules. Question 6, a tricky question this. So you've got cyclohexene, so it's got 6 carbons, it's got 2 hydrogens on every carbon, except on this one we've got a double bond, so we've just got a double bond here. And if we add hydrogen across the double bond, it gives out its exothermic by 120 kilojoules per mole. So if we had 3 alternate double bonds, like in Kekulé, we expect it to be minus 360. But it's not, it's less than that. So it's not as exothermic. So this means that when we add 3 lots of hydrogen, 3 moles of hydrogen, actually it's not as exothermic. Something that's not exothermic is stable. Something that's less exothermic than you think is stable. So benzene is more stable. Anyway, it asks us to explain the bonding and the shape of the benzene molecule. So what you've got is, you've got hydrogens on each corner, 1 hydrogen on each corner, and each carbon is bonded with a covalent bond to 2 other carbons. The fourth bond is this ring, and now we need to explain this ring. So each carbon has 3 covalent bonds to a hydrogen and to 2 other carbons, we've mentioned that, and then the fourth electron, which we call a spare electron, overlaps to form the ring. That's the best way of saying that the double single bond doesn't really exist, and that there's delocalization, there's some movement of electrons, so we don't get doubles and singles, we get movement of electrons. So the spare electron, the fourth electron that should be in a bond, overlaps. Overlaps means it's shared between each of the 6 carbons. Each of the carbons has a spare electron, and it's shared around, and it moves, and it's delocalized. So the spare electrons on each of the carbon, the fourth electron overlaps between the carbons, and the electrons are delocalized. Just something to remember. What else do we need to know for 6 marks? It's flat, it's planar. It's planar with 6 carbons in a ring, and all of the carbon-to-carbon bonds are equal length. That's how we know that they're not alternate double and singles, that they're all equal, and that's sort of explained away by this fourth electron overlapping between each carbon and being delocalized and moving around the ring. So stability. So benzene is more stable than you'd expect. So expected enthalpy of hydrogenation is if it had 3 double bonds in there, 3 doubles and 3 singles, it would be minus 360. So adding 1 hydrogen across hydrogen molecule across double bond releases minus 120. So if it were 3 double bonds and 3 singles, 3 hydrogens should release minus 360, but there's a difference of 152. So if you take the 208 away from the minus 360, it's 152 kilojoules away from the value that we'd expect. That shows that benzene's more stable. It gives out less energy when it reacts. That means it's more stable. A tough question. The enthalpy of hydrogenation of cyclohex at 1,3-diene, so that will be with a double bond and then a single bond and a double bond, so a double, single, double, is not exactly double that of cyclohexene. So cyclohexene, when we add a hydrogen across the double bond, it's minus 120. There's another chemical called 1,3-diene, 2 double bonds, one at carbon number 1 and the next one at carbon number 3, so it would be a double, single, double, and it's not minus 240. It's not double. It's not quite double. It's not exactly double. Suggest a value. So you could have anything between above 120, above minus 120, and in between minus 120 and double is minus 240. You can have anything in between that because it says it's not exactly double. So you can have anything from minus 239, which is sort of double 120. So it's not quite double, so 120 doubled would be 240. It says it's not exactly double, so it's somewhere in the middle, somewhere between any number in between minus 120 and minus 240, which would be double. Suggest a value for the enthalpy of hydrogenation of cyclohexene and justify its value. We've done that. So double bonds are separated by 1 single bond, but there may be some delocalization. So that explains why it's more stable than you'd expect. Double bonds separated by a single bond, but there may be some movement of electrons between the 2 bonds. So it might not just be double, single, double. Sometimes there's movement of electrons even between 2 double bonds separated by a single. Difficult question. Question 7. Acyl chlorides have a C double bond OCl. They're very, very reactive. They have violent reactions. They produce hydrogen chloride gas when they react with water, and it produces white steamy fumes. So this one is propanoyl chloride, COCl with 3 carbons. So this would react with anything with water and would produce hydrogen chloride gas, white steamy fume. So very violent reaction. So you've got to take extra care when you're using acyl chlorides. They react with benzene in the presence of AlCl3 in electrophilic substitution reaction. Give an equation. Well, let's have a look at the whole mechanism and I'll explain what's happening here. So the electrons in the ring need to attack this is an electrophile, so it needs to attack something that's positive charge. So you have a look at what you're putting onto the ring. So this CH3COCl is going to go onto the ring. So this part, the CH3CH2CO, is going to join onto the ring, and I need to make this positive. So what actually I do is I take the CH3CH2COCl and I react it with aluminium chloride. And aluminium chloride forms AlCl4-. It removes the Cl from here and it leaves a plus charge on the carbon. So where the carbons had 4 bonds, it's had a Cl joined to it. It's now only got 3 bonds and the Cl has gone. And the Cl minus, so the Cl and the electrons in the bond have gone on to the AlCl3. It's made AlCl4-, and it's left this carbon now without enough bonds, without enough electrons, and it's positive. Now that is going to bond to the ring. The electrons in the ring will attack that because these are electrophiles, these electron pair donors, electron donors, and it will attack this plus charge, and when it bonds it joins on. It doesn't really matter where it joins on in this case because we've got no other groups attached, so we've just joined it on here. The ring has given away electrons, so that gets the plus charge. The C plus has had electrons put onto it, so that plus has gone, and it joins onto the corner. There's also an H on each of these corners that's not shown, so now I've decided to show it, and now the plus charge is in the ring, as I've said, because electrons have moved away from the ring, and we do a horseshoe shape with the gap towards where the group's added on. The electrons go from the bond in the H into the ring, and then that's going to mean that the ring is reformed without the plus charge, and it'll have the full ring circle back in it, and the H will come off as H+. The organic product can be converted into the alcohol shown. Okay, so COCH2CH3 can be converted into an OH. In other words, I've converted a C double bond O into a COH. So instead of a C double bond O here, I've converted it into a COH and added another H. Give the name of this alcohol. So what is it? This part here is propan. So I've got propan, 1, 2, 3 carbons. If that carbon here is carbon number 1, 1, 2, 3, propan, and the OH is at carbon number 1. So at carbon number 1 I've got an OH, an ol, and I've also got this group which is a phenyl. So it's sort of propan with an ol with an OH at carbon number 1 and a phenyl at carbon number 1. 1 phenyl propan, 1 ol. What reagent can do that? Can turn a carbon double bond oxygen into an H and an OH. So you could either add hydrogen and nickel, that's one way of doing it. You do that in industry. It doesn't specify that you can't do it in industry, so hydrogen and nickel adds hydrogens. Adding hydrogens to something is using hydrogen and nickel, or you could use something called sodium borohydride. The name of the mechanism, so a hydride ion is a H-, and it would attack the C of the C double bond O, and the C double bond O would break and take electrons onto the O, and then an H+ would come along, because this is usually a methanol or dilute acid, and would make OH. Or hydrogen nickel adding hydrogen is called hydrogenation, so you could have that instead. The alcohol shown in 7.2 reacts with ethanol chloride to form an ester. So this one that I've got in this one here, this alcohol, can react with ethanol chloride to form an ester. That's because an OH group can react with a carboxylic acid group or an acyl chloride group, a COCl, and release a small molecule like water or hydrogen chloride and make an ester, a C double bond O, an ester link. So describe what would you observe when the alcohol reacts with ethanol chloride. Well, ethanol chloride, I've already said, makes white steamy fumes of hydrogen chloride. Name of the mechanism, addition elimination. So the structure of the ester would look like CO. It would have this benzene ring connected to a CH. Off it would be a CH2, CH3, and this O, then this C would be an O, and then C double bond O CH for the ethanoyl chloride. The CH3COCl would be here, and that is an addition elimination. They add on and then eliminate the molecule such as hydrogen chloride. Question 8. The polypeptide chains above are held together by hydrogen bonding, shown in figure 1. Explain how these hydrogen bonds form. So what you've got a lone pair of electrons on each of the O's, and you've got a polar bond in the N to the H, because the N is more electronegative than the H, so that means that the N has got a delta minus and the H has got a delta plus. So it's an attraction between the lone pair of electrons on the O and the delta plus on the H. We've got something called cysteine here, and cysteine has got this CH2SH, and this SH can bond with another SH. It releases the H's and forms an S to S, the sulfur bridge. So here we've got a section of the molecule CH. This CH here is this CH. It wants you to draw a bridge between these two polypeptide chains. So these are long protein chains, and you can get another bridge between the two. So the CH needs a CH2 and an SH and a CH2 here and an SH here, and the two SH's actually lose the H's and form an S to S, the sulfur to sulfur bridge. Question 8.3. The type of bond between two different polypeptide chains. So a polypeptide is another word for a protein. The order of the amino acids in the actual one protein chain, or one polypeptide chain, the order of the amino acids is called the primary structure. If a chain, a protein chain or a polypeptide chain actually bonds to itself, maybe it coils round and bonds to itself, that's called secondary. If you have two different chains bonded together, that's tertiary. So now we've got two different chains bonded together, and we've got a tertiary structure where different chains bond together and form a 3D shape. Draw the structure of the Zwitterion of a dipeptide formed by alanine and serine. Alanine on the left and serine on the right. So they're going to bond together with the carboxylic acid group here and the OH bonding with the H off the NH2, and it's going to leave a CONH or a peptide or an amide link. So the OH and one of the H's is going to release and form water in a condensation reaction and leave an amide or a peptide link between the two, CONH. Now, the last thing to do is a Zwitterion. Draw the structure of a Zwitterion. Well, let's draw it joined together first of all. NH2, CH, CH3, CO, it's lost the OH, NH, it's lost one of the H's to make water, CH, CH2OH, COOH. And then what's happened to form a Zwitterion is that H on the COOH has been lost, and it's been lost as an H+. So it loses the H and leaves COO, and because it lost an H+, it becomes a minus, and the H+ joins on the other end and becomes, instead of NH2, it becomes NH3 because it's gained an H and it's gained a plus, and the plus is actually on the N. So in question 9 we've got some bases: adenine, cytosine, guanine, thymine and cytosine. Again, it's asking us what bases they'd match up with: 1, 2, 3, 4, 5. Well, adenine matches up with thymine, and thymine matches up with adenine. Guanine matches up with cytosine, and cytosine matches up with guanine. So adenine is going to match up with thymine, so 1 is a thymine. Cytosine matches up with guanine, so 2 is a guanine. Guanine matches up with cytosine, so 3 is a cytosine. Thymine matches up with adenine, so 4 is an adenine. And cytosine matches up with guanine, so that's a guanine again. Deduce the number of hydrogen bonds formed between the 5 bases. Well, adenine to thymine forms 2. The outside 2, adenine and thymine form 2. Guanine and cytosine form 3. So that's 2. Cytosine forms 3. Guanine forms 3. Thymine forms 2. And cytosine forms 3. So I've got 2, 3, 3, 2, 3. So in total there are 13 bonds, hydrogen bonds, formed between those bases. This question is quite straightforward, 9.3. Once you work out what it's actually asking, you've got an incomplete 2-deoxyribose molecule, and you've got to draw that out just by copying it from the data book. Then you'll have an OH here, and it wants you to join on a phosphate group. Well, the OH of the phosphate group and the OH here on this carbon will form water and an oxygen link. You need the letter A to represent the base, which will come onto this point here. The next question asks you to identify which one is a primary amine, a tertiary amine and a nitrile. Well, a primary amine has got 1 carbon joined to an N. So 1 carbon joined to an N means that the N, which has 3 bonds, must then have 2 hydrogens. So a primary amine has got an N joined to a carbon and 2 hydrogens joined to the N. So it's got to have this bond in it. So your primary amine has got a peak at 3300 to 3500. Which is this one here, and that's missing in the other 2. So this one is your primary amine. Your next one to identify, well, a tertiary amine has got 3 carbons joined to an N, and we've got nothing here that's got 3 carbons joined to an N. We've got this CN here, which is a nitrile. So a nitrile, we can identify this one, the nitrile, at 2220 to 2260, which is this peak here. So that's your nitrile, and your other one then must be your tertiary amine with a nitrogen joined to 3 carbons. So your answer is your primary amine is C, your tertiary amine was B, and your nitrile with your CN in there is A. There are 3 secondary amines that contain 4 carbon atoms per molecule. Draw the formulas. We're going to do skeletal formulas of the 3 secondary amines. It's sometimes easier to do the displayed formula first and then do the skeletal formula afterwards, but it's up to you. The secondary amine means that the nitrogen is bonded to 2 carbons. So if the nitrogen is bonded to 2 carbons, it must be in the middle of the chain. It can't be at the end, otherwise it would just be bonded to 1 carbon. So you're looking for a 4 carbon chain with a nitrogen in the middle of the chain. So what can it be? It could either be 1 carbon, 2 carbon, then the nitrogen, then the 3rd carbon, the 4th carbon, or the 1st carbon, and then the nitrogen, and then the 2nd carbon, 3rd carbon, 4 carbons. You can't have the nitrogen at the end, but there's another way of drawing it, with a carbon, and then a nitrogen, and then a carbon, and 2 methyl groups from it. You can either draw it like that, or you can put the H's on the ends whichever way you want to draw it. Primary amines can be prepared from the reaction of halogenoalkanes with ammonia, or from the reduction, that means adding hydrogen to nitriles, probably with something like hydrogen with nickel. Justify the statement that it is better to prepare primary amines from nitriles rather than from halogenoalkanes. Well, when you react ammonia with a halogenoalkane, it will make an amine, and then that amine can carry on reacting with more of the halogenoalkane to eventually make a quaternary ammonium salt. So with a halogenoalkane you can get further reaction, and you can say what's actually going to be made, a quaternary ammonium salt if you want to, but further reaction will get you the marks. Draw the structure of a primary amine with 4 carbon atoms that cannot be formed from a nitrile. So a nitrile has got a C to triple bond N. So if there's a C to triple bond N, it can't then, the C to triple bond N, once you reduce it and put the hydrogens on, it won't have 2 other carbons. So it's got to be a nitrogen bonded to a carbon with 2 other carbons, or a nitrogen bonded to a carbon with 3 other carbons. Neither of these could ever have had a C triple bond to an N, because that carbon would have had 1, 2, 3, 4, 5 bonds, and this one would have had 1, 2, 3, 4, 5, 6. So there's been a triple bond N there, a triple bond carbon to N there, and that couldn't have happened unless the carbon only had 1 other carbon bonded to it. 10.5. A student dissolves a few drops of propylamine in 1 cm³ of water in a test tube. Give an equation for the reaction that occurs. Well, propylamine, amines are bases. It's got an NH2 on it. It's got 3 carbons, a propyl and an NH2. An NH2 group can accept H pluses, act as a base. So if it accepts H pluses from H2O, this is what happens. Propyl, CH3, CH2, CH2, NH2, and from the water it accepts an H plus because it's a base, an H plus acceptor. If it accepts an H plus from the H2O, the H2O has lost an H and it's become minus. Observation, if that's a base, then it's going to go blue, the indicator, so the indicator goes blue. Propylamine can be prepared from a process involving the reduction of nitrobenzene. So benzene, a benzene ring with an NO2 on it, using tin and an excess of hydrochloric acid. Another way of getting NO2 groups on a benzene to an NH2, phenylamine and amine, NH2, would be to add hydrogen and nickel. But in this case they want to add tin and hydrochloric acid. It's another way of doing it. Give an equation for the reduction. That means removing the O's off the NO2 group and making NH2s to form phenylamine. Use H square brackets to represent the reducing agent. The reducing agent is the tin and the hydrochloric acid that's removing the O's from the NO2 part of nitrobenzene to make NH2. Explain why aqueous solution is obtained in this reduction even though phenylamine is insoluble in water. Okay, first of all let's do the equation. So you can either write that as C6H5NO2 or you can draw it out as a benzene ring with an NO2, whichever you prefer. Now when those become NH2s, the O's become waters, and I'll need 2 waters to balance the 2 O's. Therefore I'll need 1, 2, 3, 4, 5, 6 H's, and I'll represent that with 6. And the square brackets H means that's coming from the reducing agent from the tin and hydrochloric acid in some way. Explain why an aqueous solution is obtained in this reduction even though phenylamine is insoluble in water. That's tricky, that. This is a base. NH2 is still a base, and the base will react with hydrochloric acid. And if this NH2 reacts with hydrochloric acid, that will make NH3 plus, take the H plus from the hydrochloric acid, NH3 plus and Cl minus. So it's going to make NH3 plus Cl minus, which is ionic and will dissolve in water. Tricky part of the question, that. There are several isomers with the formula C6H16N2. One isomer is shown here. The number of peaks in the 13 carbon NMR spectrum of the isomer, you've got to work that out. So how many different carbon environments are there? Well, it's symmetrical from the N onwards, up and down. So those two carbons are the same environment, so that's one. Those two CH2s are in the same environment, that's the second one, both bonded to that N. Here's a third one, a CH2 bonded to an N, and a CH2 bonded to an NH2. So there's 1, 2, 3, 4. Splitting pattern of the hydrogens labelled alpha here, so the splitting pattern here. Well, they haven't got any hydrogens to the left, but they have got hydrogens to the right. They've got two hydrogens to the right, so two hydrogens bonded onto an adjacent carbon means that that will be a triplet. Explanation is the neighbouring carbon atom, the carbon bonded to the CH2, has two hydrogens on it. Draw the structure of an isomer of C6H10N2 used to make nylon 6,6. Well, what's nylon 6,6? Nylon 6,6, it's got an amide link in there. It's a polyamide. The polyamide, it's an amide or a peptide, whatever you want to call it. Chemists call it an amide, so it's a polyamide, and it's been formed from an NH2, an amine on one end, and then 6 carbons, 6 CH2s, and then an NH2 on the other end. And then on the other monomer, you've had a carboxylic acid group or an acyl chloride group. If it were a carboxylic acid group on either end, it would release water. If it was an acyl chloride, a COCl, it would release HCl. So there's been an NH2 on either end of 6 carbons, 6 CH2s, and the NH2 has reacted either with a carboxylic acid group to lose an H and an OH to make water, or the NH2 has reacted with an acyl chloride to make H and a Cl. So that's the formula of the monomer here used to make nylon 6,6, either then with another monomer with 6 carbons in and 2 carboxylic acid groups at either end, or 2 acyl groups at either end. Question 11.3. Draw the structure of the isomer of C6H10N2 that contains two primary amine groups. So what's a primary amine group? Primary amine means that the N is bonded to one carbon only. A nitrogen has 3 bonds, so the other 2 bonds must be H's. So it must be NH2 and a carbon. And it's got 2 of these NH2 groups on there, and yet it's only got 2 peaks in its carbon-13 NMR spectrum, even though it's got 6 carbons. That gives you a clue. It would only do that if it's symmetrical, because the atoms, the carbons on one side, will be in the same carbon environment as the ones on the other side. Because if it's symmetrical, then you get carbons in the same environment because they're bonded to the same atoms. Now, if it's a very, very long chain, the ones in the middle would be different environments to the ones towards the end. So it's quite a short chain that's symmetrical with 2 NH2 groups. Now, a little bit of trial and error will bring you to this then. It's just 2 carbons long with 2 NH2s, 2 primary amine groups, and 4 methyl groups, and perfectly symmetrical. If it was a very long chain, then the ones in the middle would be different, have different carbon environments. Every time you moved along a carbon, it would have a different environment to the ones towards the end. So it's got to be quite a short chain, and those 4 methyl groups then have 1 peak, and then the 2 carbons in the middle are in the same environment, have a second peak with 2 amine groups, primary amine groups. Draw the structure of the isomer of C6H10N2 that contains 2 tertiary amine groups. Now, a tertiary amine group has a nitrogen bonded to 3 carbons and only 2 peaks in its carbon-13 NMR spectrum. So again, it's quite small, and it's going to be symmetrical. And so by sort of a little bit of trial and error, you should be able to work out it looks a little bit like this. A nitrogen with 3 carbons around it, 2 methyl groups, another carbon, 2 methyl groups, another carbon, and then the 2 carbons bond. A tertiary amine, 3 carbons around it, quite a short chain, symmetrical, so each of the methyl groups are in the same environment, are 1 peak on the NMR spectrum, and those 2 CH2 groups are in the same environment as well and produce a second peak in the carbon-13 NMR spectrum.